Hey everybody, we're going to be going over how to solve that FRQ that we did in class. So let's get going. All right, so I need to get this down here. And so here is our FRQ, right? We have a 0.5 kilogram cart. It's moving down a straight horizontal track, so that is super important. It's horizontal. The graph is Vx versus time, and it's given down below. Okay, so this is given to us in the problem. We have a velocity versus time graph, and then indicate every time t for which the cart is at rest. And I put that little Vx equals 0 there. So indicate every time for which the cart is at rest. This is a velocity versus time graph. So if I want to know when it's at rest, I need to know when the velocity is 0. So we just follow this path, and then we see the graph is 0 right around there. And then also we'd be following it. It's not 0, not 0, not 0. And it's 0 the only other time right there. So our answers, we want to have time equals 4 seconds and time equals, what is that, 15, 16, 17, 18 seconds. Make sure you put those units on the answer. Right? We don't want to just have t equals 4 and t equals 18, because just don't leave it in the hands of the grader, right? Don't leave anything up to them. All right, so indicate every time interval so for which the speed of the cart is increasing. So remember, speed is important here. That is a scalar quantity, which means it does not care if it's positive or negative. All it cares is if the magnitude of our velocity is increasing. The only time that happens is if when we're following this graph right here, if the graph is going away from 0, then it's going to be an increasing magnitude, right? Or speeding up in this case. So the only places where that happens are right here. We got this little line segment, right? So that's from 4 all the way to 9 seconds. And then the only other time that our graph is going away from 0 is from there to there. So this is 18 to 20. And that's seconds, right? So I could put it down here. 20 seconds right there. So let's see, from 4 to 9 seconds would be one of our answers. And from 18 to 20 seconds would be our other answer. Okay? All right, C. Determine the horizontal position of the cart at 9 seconds. So let me just erase some of this real quick. At 9 seconds, that's right there. All right? So 9 seconds is there, and I know that this is a velocity graph, so the area of our velocity graph is equal to the displacement. Okay, so when I find the area, then that's going to give me how much it's moved. So first thing I would do is I would just shade in all the pieces that I need to find the area, and then I need to actually find the area of these. So this is a triangle, and its base is 4 seconds, and its height is 0.8 meters per second. And so that area right there is 1.6 meters. And then I go down here, this is 1/2. The base goes from 4 to 9. So the base is 5 seconds. And the height is negative, because it's down below, -1. Okay, so that gives me an answer of negative 2.5 meters. All right, so I know right now the displacement is just adding up those areas together. That's 1.6 plus the negative 2.5. That's going to give me a overall displacement of negative 0.9 meters. All right, but that is not the final answer. Remember, that is only the displacement. Then part C, it throws this little wrinkle in there, and it says if the cart is located at an initial position of 2 meters, what is it? It's asking us what is the final position, right? So remember, displacement just talks about how much it moved. So if I want to know the final displacement, I just add my initial position to the displacement, right? I started at 2 and I moved negative, so backwards, 0.9 meters. So what is my final position? Final position is 1.1 meters. Okay? So that's where I'm at for C. For part D, we have, let me get this, I don't know why it's being weird. Don't do that. There we go. On the axes below, sketch the acceleration versus time graph for the cart. So remember, the acceleration is just going to come from the slope of each of these little line segments. So I need to find what is the slope. So when I'm looking at this graph, I'll draw it in, we'll go yellow. All right? Over this first 9 seconds, that is a negative slope. So I know I already need to have a negative constant acceleration. And I just need to find what is the slope of that line. Okay, so it goes down, and we can just look at this part to find the slope, right? It goes from 0.8 to 0. So it goes down, just do a little scratch work over here, from 0 to 9. It goes down 0.8 meters per second, and it took 4 seconds. So that is an answer of negative 0.2 meters per second every second. So what I would have is that, remember, that's that whole from 0 to 9 seconds. So from 0 to 9, I would draw my flat constant acceleration value right there at negative 0.2. All right. Then I take a look, and my next line segment I need to find the slope of is right there. Okay. So from 9 to, that's 12 right there. From 9 to 12, it went from negative 1 to negative 0.4. So it went up 0.6 in 1, 2, 3 seconds. So from 9 to 12, it went up, so positive 0.6 meters per second in 3 seconds. Right, so what is that? That gives me, what is that, positive 0.2? So I find positive 0.2 right here, and I give it a line like so. Okay, then I go back. Well, flat is nice and easy. With flat, so from 12 to looks like 17, that is a slope of 0. So from 12 to 17, slope of 0, 12 to 17. Okay, and then from 17 right here, all the way up to the top at 20, it's going to be the same line right there, right? So the same line, I can use any points on that line to find the slope. So let's just make it easy. Let's do this first one. In 1 second, it goes from negative 0.4 to 0. So from From 17 to 20, it goes, that one little part we looked at, it went up 0.4 meters per second in 1 second. Okay, that would give me a positive 0.4. So I find positive 0.4, and I draw right there. Okay, and then this last part is flat. That's a horizontal line, so my acceleration would just be 0 again. And that's all the way to the end at 25 seconds. Okay, so yeah, I know, like for this first one from 0 to 9, I only used the little 4-second time right there, but I can use, whoop, oh, it just happened. I can use that slope, right? this whole line has the same slope. So I just use the first 4 seconds to find what the slope is, and then that slope is the same for that whole line segment. Okay. So moving on to E, we have a projectile type problem from t equals 25 seconds until the cart reaches the end of the track. The cart continues with a constant horizontal velocity. Let's make it red again. Actually, let's go. Yeah, we'll go yellow again. We like yellow. Constant horizontal velocity. The cart leaves the end of the track and hits the floor, which is 0.4 meters below the track. Determine each of the following. So I'm going to draw a little picture because those always help me. Let's go white for the picture. Here's the end of the track. Basically a table. Right, little cart goes flying off at some initial velocity. The cart goes and hits the ground. This thing is 0.4 meters above the ground. And the part 2, it's asking us to find the displacement. But part 1 is saying, what is the time that the actual car is in the air for? So let me erase this little part. All right, I like the stroke eraser. Here we go. Let's figure out what we got. I know, so let's make our list of info in the X and Y direction. I know that when something is projectile, it always has these rules. In the X direction, has 0 acceleration. In the Y, it's negative 9.8. All right. I can figure out initial velocity because it says it keeps the same constant horizontal velocity that it had at the end of 25 seconds. So if I go back up here, right, I can see that at 25 seconds, this cart was going 0.8 meters per second. And then that 0.8 stays the same until the cart goes off the table. So this cart goes off the table at 0.8 meters per second. And in the Y direction, right, if it leaves horizontally, that lets me know the Y is 0. Let's see, what else do we know? We know displacement. We don't know it in the X yet, but we know in the Y this thing falls down, so negative 0.4 meters. And we are being asked to solve for time. So now is where I would go look at my equation sheet, right? And I can go, this is the first page, not really helpful. We can go to the second page, and from here, right, I see in the top left, let's make this thing draw again. There we go. There's my kinematic equations in the top left, and they look just a little bit different. So I always have students, when they first get these equation sheets, just kind of modify them a little bit. Scratch this out and change that to displacement. And then scratch out that part and make this also displacement. Okay, so I would be looking which one of these equations can I use to solve for that, all right? And it ends up being the second one, I do believe, because we have acceleration, initial velocity, displacement, and time. Yeah, so I would choose the second equation. I'm dealing in the Y direction, so I'm just going to use Y instead of X. Okay, and my goal is solve for t. So make your life easy. If this initial velocity is 0, when we plug in 0 there, that whole term goes to 0, right? So I end up with displacement is equal to 1/2 at squared. Time, we do a little abracadabra. If I want to solve for time, I'm just getting this variable alone, and then it ends up being boom. And then I plug and chug. Plug in my values. 2 times negative 0.4 all over negative 9.8. I don't know what that is off the top of my head. Let's see. You pull out your calculator, and I got, what is the square root of 0.8 divided by 9.8? 0.09. That doesn't seem right. Oh, you know what I did? Made dumb calculator error. I didn't use a parenthesis. So here, I'll show you what I'm talking about. Why is it so gigantic? There we go. I would need to do the 0.8 divided by 9.8 equals, and then square root it, 0.285. So 0.28, 0.29. So not that. 0.285 seconds would be our time. And then the horizontal distance. So now I'm being asked basically, what is that horizontal displacement right there? Okay, and right there we know we have all of the same variables. Remember, we just figured out what the time in the air is. It's 0.2, we'll say 0.29. Okay, so we're now being asked to solve for this last variable. So we're going to use the exact same equation. Now, if acceleration in the x direction is equal to 0, then I'm able to get rid of that whole acceleration chunk because it becomes 0. And I'm left with initial velocity times time, which is 0.8 meters per second times 0.29 seconds. And let's figure out what that is. So all of this times 0.8. 0.22 meters. Boom. All right. If you want to take a look at the rubric, it is posted on the Google Doc that we use for our class, and you can take a look at it there. All right, ladies and gentlemen, I'll see you later.